Okay, I think it's time. You may start, and the people will come slowly as usual. Please, Christina.
All right. Thank you very much for the opportunity to speak again. So I'm presenting the third lecture of Intrinsic Flat and Gromov-Hausdorff Convergence. Lectures 3 and 4 sort of run contiguously with the same set of slides. So we can go as slowly or as quickly as anyone wishes. Please stop me if you have a question. Remember that in lecture 1, we reviewed the notions of CK, C0, Lipschitz, and Gromov-Hausdorff convergence. Then we introduced the intrinsic flat convergence, which has two notations, SWIFT, or just a calligraphy F, and volume-preserving intrinsic flat convergence, which is flat convergence with the additional requirement that the global volume converges to the global volume of the limit space. And then we also introduced this simpler notion, volume above, distance below convergence, which has been shown to imply the volume-preserving intrinsic flat convergence. But this one is easier to test things with. In the second lecture, we considered open problems and scalar curvature, particularly three-dimensional manifolds with scalar greater than or equal to h in their limit spaces, which geometric properties of scalar greater than or equal to h persist on their limit spaces, which rigidity theorems for M3 with scalar greater than or equal to h have geometric stability. One nice summary of what happened in lecture 2 that Andrea Mendino commented at the end of the talk was how sectional curvature seemed to be captured with distance alone because of the triangle comparison. Ricci curvature needs volumes and distances, and it seems that scalar needs notions of volumes, areas, and distances, at least in 3 dimensions. Volumes, areas, and distances were involved in the various rigidity theorems for scalar curvature. So we wanted a notion of convergence that keeps track of volumes, areas, and distances, and produces a limit space which has the possibility of capturing some of these properties. The proposal is that volume-preserving intrinsic flat convergence is the notion that would best capture these 3 properties, and it's being tested in the various open problems and has been shown to be worthwhile in a number of special cases. So today's lecture, I'm going to present techniques to apply in order to prove convergence, so that if you're interested in working on some of these open problems, you'll actually know the methods that you can use to prove intrinsic flat and volume-preserving intrinsic flat convergence. You've learned a lot about Gromov-Hausdorff in the other lectures, so I actually reduced the amount of Gromov-Hausdorff convergence I'm covering in this course. All the papers are in the same website here, which I shared on the chat before. And I also put my notes at the top of this website for this particular course for now. I will move them later over to notes for talks. But anyone who needs to access them for now can see the most up-to-date version here. So let's recall that volume-preserving intrinsic flat convergence is a notion where you assume you have intrinsic flat convergence and volume converging for the whole manifold. And that the definition of the intrinsic flat distance between 2 Riemannian manifolds, or more generally, integral current spaces, which we will explain further in this talk, is that you place both of them inside a common metric space Z, and then you find a sort of volume between them. B is a integral current or submanifold of 1 dimension higher that sort of fills in the space between them, but the boundary of B does not have to be exactly M1 minus M2, keeping track of orientation. It can have an extra part A, that's part of the boundary of B, and then what we do when we estimate the intrinsic flat distance is to take the mass of A, which is kind of like a weighted volume, plus the mass of B, which is also kind of like a weighted volume, but it has some extra terms. We're going to learn exactly what this means, exactly what A and B are in full generality in this lesson. We've been doing it somewhat vaguely until now. So let's talk about the history of the flat norm, because as I said, the intrinsic flat norm is built on the notion of the flat norm. In 1957, Whitney introduced the flat norm between submanifolds Ni that are both sitting in Euclidean space. They're both the same dimension. In my picture here, they're both one-dimensional. N1 and N2 have an orientation, and the flat norm, which is written with the flat symbol from music, is the infimum of the mass of A plus the mass of B, where A and B are chains sums of weighted submanifolds such that A plus boundary B is equal to N1 minus N2. So that's the whole idea, this exact summing up of weighted submanifolds is all Whitney's idea, and he used chains in order to implement it. Whitney did not, this is in his book, I think it's Geometric Measure Theory. The problem with the notion of chains is that he did not in 1957 attain a compactness theorem for sequences of Ni with various bounds. When do you get a flat limit? So in 1957, there was no way to find a subsequence that converged for this kind of a sequence. Federer and Fleming in 1959, they used Whitney's definition, but they changed the A and B to be what's called currents acting on differential forms omega in Rn. So they view a submanifold phi of M as an M current, and they use this notation, phi push forward of M with these brackets around it to indicate how the submanifold acts on a differential form. So omega is a differential form of dimension M in Euclidean space of some very high dimension capital N. That's what you should imagine. Originally, perhaps you might say it surfaces in Euclidean 3 space, but we should really be picturing that our ambient Euclidean space is very high dimensional. So phi, the push forward of M, how it acts on a differential form, is defined as integrating over the submanifold's image, the differential form, which is the same as pulling back to the manifold the pullback of the differential form, where omega is an M form. Now here's an example of an M form. M F d pi 1 wedge wedge d pi M is an example of an M dimensional form, differential form, where all of these are smooth functions. And if you wanted to understand what does phi number M mean acting on that form, it's an integration over M. What does this pullback mean? It means you're taking F following phi, so that now we have a function defined on M. F following phi is a function on M. It's a nice smooth function. And then d of pi 1 following phi wedged up to wedge d phi M following phi M following phi. So each one of these is now a differentiable function from M to the reals. And so you can take its differential d and you can take wedge products. So this is a well-defined notion and is an example of how this acts on a particular differential form that comes in this form. Remember, differential forms do not have to only have that form. They can be sums and linear combinations of things of this form, where the pi 1 to pi M change, and so does the F. Given a current T, so an M current T, they define boundary of T to be boundary T acting on a differential form is T of D of that form. And that's designed so Stokes' theorem works. So let's look at this. Boundary of, if we look at a submanifold N, omega would be N of d omega by this definition here, which means integrate over N of d omega, which by Stokes' theorem is integrate over boundary of N of omega, which then means that this is the same as the current defined by the boundary of the submanifold. So if you have a submanifold with boundary, this notion of boundary for current interacts perfectly with the notion of boundary of the submanifold. Notice it's one dimension lower than the dimension of the submanifold. Again, let's look at what D means. D, because we have to understand if omega was F pi 1 wedge up to pi M, what would be D of that? Well, it's just dF wedge d pi 1 wedge up to d pi M. Right, so that's how you find the exterior derivative D of a differential form. All right, so I'm moving up the information I just gave you. This is the Whitney definition. This is Federer-Fleming and how they define something called the integral current. Now, they want to extend the notion of submanifold, so they say an integral current is a special kind of current. It's not necessarily from a submanifold. It's an integer rectifiable current whose boundary T is defined in this way, is also an integer rectifiable current. So what does integer rectifiable mean? An integer rectifiable current T has a countable collection of pairwise disjoint bi-Lipschitz charts phi I that go from Borel sets AI inside Rm 2 phi I AI inside R capital N, which is a very large dimensional space, is how you should imagine it. So AIs are in Rm of the same dimension as the current that we're trying to define. And you're looking at images of them, but you're only looking at by Lipschitz images. And you can make them pairwise disjoint. And by Lipschitz, the original definition of integer rectifiable did not require this pairwise disjointness or the by Lipschitzness. But one can prove that the original definition is equivalent to one in which you require that they're pairwise disjoint. That means the images are pairwise disjoint and that each piece has a by Lipschitz chart. In addition to the rectifiability here, this integer part means that we have weights, AI, in the integers, such that we can write our current T acting on a different differential form to be the sum of AI times the integration over AI of phi I star omega. So here's the little submanifold notation that we had from before, but now our phi I is only by Lipschitz. That's basically all right. Oh, wait, let me go back. The reason phi I star omega is all right to be only by Lipschitz and not differentiable or smooth is because a Lipschitz function is differentiable almost everywhere. So we can still define d pi 1 and d of pi following phi. All of that is defined almost everywhere. And since what we're doing is integrating, the fact that the d, the differential, the exterior derivative, is defined almost everywhere still makes this integral defined, well defined. Now that's an integer rectifiable current. An integer rectifiable current has integers and it's rectifiable. Rectifiable means countable collections of bi-Lipschitz charts. Rectifiable sets have countable collections of bi-Lipschitz charts as well. Rectifiable currents are just like rectifiable sets, except that they're acting on a differential form and using the same formula we used for submanifolds. And then to actually be an integral current, we have the double condition. We require that the current itself is integer rectifiable and that its boundary T, defined this way, is also integer rectifiable. That means that the boundary has a pairwise disjoint collection of bi-Lipschitz charts, but it's not the boundaries of these charts. That's not required. The total boundary of these charts could be infinite and might not have a converging sum here. The AIs are not required to have finite perimeter. What it is saying is that if you sum these all up and you act them on d omega and you find out that there's this action that's well defined to define t of d omega, and you can find another collection of charts such that it is a sum of bi's integral over sets bi of phi of different phi's star omega. So remember that being integral current just means that you're able to use Stokes' theorem, but the same collection of charts is not used. It might be used, but it is not necessarily used in order to find out why the boundary is also integer rectifiable. Any questions? Let's check the chat. Direct message. Okay, no. All right, so this is the 1950s. This is the start of geometric measure theory. In this world, they define the mass of T to be with this double bar T acting on Euclidean space to equal the sum from I = 1 to infinity of these integer weights. Now they're given absolute values times the Hausdorff measure of the images. Okay, so the mass of the space is a sum, it's a weighted volume. This M here matches the dimension of the current. And then the compactness theorem of Fleming, which is why this technique was so useful, is they proved this compactness theorem, that if integral currents Tj have support of Tj contained in a compact set, mass of Tj less than or equal to V, and mass of boundary Tj less than or equal to A, then there exists a subsequence Tjk and an integral current T infinity, such that Tjk minus T infinity in the flat norm, this flat norm here, but with A and B chosen to be integral currents, converges to 0. the important aspects of this compactness theorem is that they understand the property of the limit space. The limit space is also an integral current. Saying that the support of Tj is contained in a compact set is saying that when you test T restricted to a compact set, that's the entirety of T, is the best sort of way to say it. They're not, the images of these charts aren't going off somewhere else. They're all confined to a compact region inside this large Euclidean space Rn. Furthermore, the boundaries of Tj flat converge to boundary T infinity. This should not be the cal F. This should be their flat. Okay, the boundaries will converge. And the limit of the masses is bigger or equal to the mass of T infinity. So this is an extremely useful property, which allowed them to then apply this compactness theorem to study the plateau problem, looking for a sequence of submanifolds whose, say you're sitting inside Euclidean 3 space, you're given a curve, a closed curve, and you're asking, is there a submanifold that's minimizing the area among all submanifolds with that boundary? So then they could take a subsequence of the submanifolds getting closer and closer to achieving that boundary. The boundary would be fixed in that case, so they would have this bound. The areas would be converging down to the infimum of areas. So this bound would exist. They cut and ensure to have they in a compact region using a cutting process. And then they have that there exists a subsequence and an integral current T infinity such that this goes to 0. And because of this, the mass of the T infinity is actually equal to the infimum of all those areas. So they solved Plateau's problem, but the limit that they found was not necessarily smooth, it was an integral current. And then this also solves many higher dimensional versions of the same thing. And furthermore, they show that Tj omega converges to T infinity omega for any differential form omega. This is actually quite easy to see once you have the A's and once you have this flat distance going to 0, you have AJs and BJs such that their masses are going to 0. And then you can test omega with them and you'll see that, yeah, sure, Tj of omega converges to T infinity of omega. All right, so that's all these beautiful properties. And you would like, when we were trying to define intrinsic flat, we were hoping to have just as many beautiful properties true for sequences of Riemannian manifolds intrinsically. All right, so we would like to imitate Gromov's theorem, where he says, oh, you have sequences of manifolds, you embed them into a common metric space Z, and you take a Hausdorff limit. And sort of like that rough idea. And we wanted to do something similar. Could you do that with a sequence of Riemannian manifolds? But putting them into a common metric space Z is not enough to apply Fleming's theory, because they have to all lie in a high dimensional Euclidean space and not infinite dimensional, just high dimensional, high bounded dimensional Euclidean space. So in order to extend this notion, we need actually to have all of this working on a complete metric space Z. So one has to wait to develop the theory until Ambrosia and Kierheim could extend it to complete metric spaces Z. So let me just copy everything I just told you. I'm just putting the key facts from the last board here up on the board so we can compare. So we can, in order to extend this definition, where the R capital N will be replaced with Z. Let's capture the key points. Currents in Rn act on differential forms. Given a smooth phi from Rn to R, Mn to Rn, we have this notion to find on a differential form of this for F pi 1 wedge. This is how it looks. We've discussed this one already. And given a current T acting on a form, this is how we do the boundary, and this is what D of a differential form is. And you notice how we're using the differentiability. This differential form exists on Rn. We're using the fact that we can take D of pi 1. But we really only need it to be true almost everywhere. So Lipschitz should be good enough. And here we need df wedge now. That's a little more tricky. What is this differential? Wedge this stuff. Okay, again, it seems like Lipschitz should be enough. So what DeGiorgi proposed in 1995 was for a complete metric space Z, we want to define currents. So what we're going to do is imitate these two facts. Replace the differential forms f d pi 1 wedge d pi m with tuples f pi 1 dot 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 pi m, such that f from z to r is a bounded Lipschitz function and pi I from z to r are Lipschitz. Now, all those beautiful properties of differential forms that you learned, where you can permute them and you get negative 1 to the order of the permutation, all of those properties are lost. There is nothing in here in his definition of tuples that says that if I reorder my pi i's that I alternate my sign with switches of pi i's. He's just saying abstractly, we're going to talk about tuples. And this tuple is different from, completely different and unrelated to f, where we've reordered the pi i's. There's no relationship whatsoever. Then he says, given a Lipschitz function phi from mm to z, define a current acting on tuples of the form phi number m of f. Now he wants to imitate this one here that was in Federer-Fleming. It's going to imitate this. Integration of m, exactly the same. He's just set up the action on a tuple to match this exactly. So a submanifold acting on a tuple will have all those alternating properties because differentiation here on M, which is smooth, this differentiation, when you reorder it, will have the -1 to the sign of the permutation. So the tuple itself doesn't have permuting properties, but the current defined by a submanifold, a Lipschitz submanifold, does have those alternating properties. And given a current T acting on a tuple omega, he wants to define boundary T omega equal T d omega again, but now he needs to define what is d omega. So we need to define d of f, this tuple here. What should d of this tuple be so that it looks almost exactly like this one? If it looks like this one, then we should get Stokes to work. So let's see, we need f pi 1. The d is going to take us up. So it's going to be an m plus 1 tuple, one higher. And if you think about it, this is really 1 df wedge d pi 1 wedge d pi m. There is a function, the constant function 1 in front of here. And so DeGiorgi decides that d of f pi 1 to pi m should equal 1 f pi 1 to pi m. If you do this, define it this way, then phi number of the boundary will work out exactly as we want from Stokes. Okay, so now I'm just sliding up what I have here. Everyone just look at how it comes exactly from Federer-Fleming, and it's designed to work. I'm going to move up the DeGiorgi information to the top of the slide. So I've slid up the DeGiorgi information. This is exactly what we already had. Okay, Ambrosia and Kierheim 2000 define an integral current T is an integer rectifiable current such that boundary T is also integer rectifiable. All right, that's exactly the same as Federer-Fleming, but let's just look a little bit. What was integer rectifiable? T is countably many pairwise disjoint by Lipschitz charts and weights AI and Z such that, okay, almost exactly as in Ambrosia Kierheim, T of f pi 1 to pi m is going to be integration of AI f following phi, d, and all this. Now, AI is a Borel set sitting in our M, so you can integrate over it. F pi 1 to pi m are Lipschitz, and the phi i's are Lipschitz. So there should be a subscript I here on all these phi's. This is well defined because Lipschitz functions are differentiable almost everywhere. So even though our tuple is a collection of functions f from z to r and pi I from z to r, and we have no notion of taking df on z or d pi I on z, we're doing the d, the exterior derivative, after we pulled back to AI. AI is sitting inside a Euclidean space of dimension m. So this d is well defined. This wedge product is well defined. So all the differentiability has been pulled back and is acting on the domain of the chart. And then they also require that you don't want to include any of these sums unless it's finite. So they are requiring that T has finite weighted volume, which takes the form of I equal 1 to infinity of the norm of AI, the Hausdorff measure of the phi I AIs. This is well defined on Z. Hausdorff measures we talked about already, and absolute value of AI is, of course, defined. If this sum is finite, they say it's integer rectifiable. So this finiteness was not required in the work of Federer Fleming, but it is required in Ambrosia Kierheim. They require this upfront as part of their definition of integer rectifiable. They actually write it differently. I wrote an equivalent thing that's easier to state than their definition. So to be an integral current, you have both T has this and boundary T has another set of charts. And the other set of charts also has to have this to be finite. Any questions? All right, I'm going to slide this up. Oh, wait. Let me just warn you, mass is not weighted volume in Ambrosia-Kierheim theory. So before, this was the same as the mass in Federer's theory, but it's not this weighted volume in Ambrosia-Kierheim theory. We're going to have to define the mass differently because otherwise the lim-inf of masses will not be bigger than or equal to the mass of the limit. Okay, so in order to have that nice property where the lim-inf of the mass of the sequence is greater than or equal to the mass of the limit, they needed to define mass differently. We'll get to that soon. So I've just lit up everything I had there. And now let's define how Ambrosia-Kierheim defined the mass. So the mass is mass of T is equal to the mass measure of T of Z. So this is a measure that's being defined. I'm going to have to define what this measure is, where this bar T equal mu T is a mass measure of T, which is the smallest measure mu such that phi number m of a, I really should have written this in the tuple form, f pi 1 comma pi m, okay? Phi number m acting on a tuple is less than or equal to the product from I equal 1 to m of lip pi I times integration over phi m of f following phi mu. So you notice that, remember that pi number of m acting on this tuple here, should be written as a tuple, not a form, would normally have f following phi in the absolute value, like this, right? And then it would have d of each of these. And then, if it's d of these, then that means each one is less than or equal to lip pi I, right? That's a change of variable sort of overestimate. And then there should be some measure, the volume measure. If it's a Riemannian manifold, this would be lip pi I, absolute value of f following phi, volume measure of the manifold would be an upper bound for this. It would be the smallest upper bound for this, testing all possible values of f pi 1 to pi m. And what we're saying here is that the mass measure has to be the smallest possible measure that works in the spot where the Riemannian volume would have been. This definition is what's strong enough to prove that we'll have the lim-inf of masses greater than or equal to the mass of the limit. There's a serious theorem way deep in their paper, like section 6, that says that the mass measure is lambda times theta times the Hausdorff measure restricted to the set of T. Theta is just a function on the space Z, where theta at a point P is equal to AI if P is in the image of the chart AI. This works because we've just required pairwise disjoint by Lipschitz charts. So if you define theta to be like this, to be equal to AI if you're actually within the chart for AI. I don't care what, theta doesn't need to have a value outside the image of the charts, because here we're only looking at the Hausdorff measure restricted to the set of T, which is only positive for points inside the image of the charts and in the closure of the image of the charts. Lambda of P is some number between a little constant depending on dimension and a big constant depending on dimension. These two constants are computed as what's called an area factor, and we'll discuss this some more. And the set of T is the points in Z such that the limit as R goes to 0 of this mass measure of a ball divided by R to the M is greater than 0. So these are the points of positive density. We're not including cusp points. We're only including points of actual positive weight. So HM restricted to set T is saying we're basically studying Hausdorff measure, restricting ourselves to set T. Any points that don't lie in set T do not contribute to this mass measure.
Christina,
yeah.
Andrea, there's one question. The theta is AI or is the absolute value of AI? So can it be negative?
Yes, yes, of course. It's the absolute value of AI. This is
okay,
a
thanks.
typo. Thank you very much. Thank you so much. Yes. A kindly stated correction. Anyhow, yes, it should be absolute value of AI. We want a positive measure here. And let me add one more point here. Because this lambda p is between these two constants that are not bounded away from 0 and infinity, this mass measure is bounded on either side by weighted volume. Okay, so if you can control, it's hard to estimate this mass measure. Really very hard to figure out lambda. Figuring out this lambda function is very difficult and involves tangent cones and things of the sort. But for most proofs, you just use the fact that lambda is between these two constants, and you just need to figure out the theta HM restricted to set T part, which is much easier to work on. So that's what's important to keep in mind, that we're really, thanks to this bounds here on the lambda, we're really only needing the weighted volume in order to complete our estimates from above or below. So to find this limit, for example, the weighted volume is enough to check if this is greater than 0. And that makes it much easier to figure out the points in set T. The only reason you need this complication of having this lambda is because if you want the limit for the mass measures to actually equal some bigger than or equal to something, then you really needed the mass measure to pull that off. All right, so I think I just lit up. Yeah, all I did was slide up the information from the last slide, tighten it up here, so we can refer to it when I introduce the next point. This set T is proven by Ambrosia Kierheim to be countably rectifiable. In fact, the Hausdorff measure of the set T, taking away the union of these charts here, is equal to 0. So the charts that are used to define the integer rectifiability are in fact charts that can be used to cover set T almost everywhere. The dimension here of this almost everywhereness is Hausdorff dimension M, where T is M dimensional. It is not the Hausdorff dimension of the capital space Z that we're sitting in, not inside that metric space Z. It's the dimension of the T, of the submanifold. They proved the compactness theorem, the same one as Federer-Fleming, but with an entirely new proof, and their proof also provides a new proof for Federer-Fleming's compactness theorem. So if you want to learn all this geometric measure theory, I do recommend just going to Ambrosia and Kierheim's 2000 paper and learning everything there. And if you happen to be in Euclidean space, that's fine. You can use this theorem anyway. In the case where Z happens to be Euclidean space, lambda is 1. Okay, so this will be consistent then with the Federer-Fleming theory. Compactness theorem of Ambrosia Kierheim says if integral currents Tj have the set of Tj contained in a compact set, the mass of Tj less than or equal to V and the mass of the boundary Tj less than or equal to A, then there's a subsequence Tjk and an integral current T infinity such that Tj omega converges to T infinity of omega for all omegas. So testing it on all tuples omega, you get Tj converging to T infinity. Then you can show the boundary of Tj's converge to the boundary of T infinity, testing it on all tuples of 1 dimension smaller. So I used eta to represent a tuple of 1 dimension smaller. And you get the limit of the masses works. This is actually proven in multiple theorems in their paper, but I put it all at once so we have it in nice and concise, everything that we have at once. The beauty of their compactness theorem is they've extended the notion of a submanifold sitting inside a complete metric space. They've extended Federer-Fleming's compactness theorem to the setting where you're just sitting in metric spaces. And they still have that if you have a sequence Tj converging to T infinity, then the boundaries converge and the masses the limit for the masses is bigger or equal to the mass of the limit. All right, so we have all this. This is beautiful. This is 2000. And so Stefan Wenger, who was a postdoc at NYU at the time that I was working with him, he was working with Gromov, and he was interested in looking at this problem as well. He was an expert in Ambrosia Kierheim theory because he was Lang's student. And he wanted to help with the project of proving the intrinsic flat distance, to define an intrinsic flat distance that would be a natural definition that comes out of combining Gromov's idea of taking infimums over embeddings into metric spaces of overall distance preserving maps, but then using a flat distance inside the limit space. So here we go. There it is, the same definition I've defined before. But now the key thing is that we're using integral currents a la Federer-Fleming, Ambrosio Kierheim's integral currents here for our A's and B's. So I had promised you all along that I would tell you what rigorously this infimum was, and this is now the rigorous definition. The push forward of a Riemannian manifold, you know what it is now. You know what this means, how it acts on a tuple. And now we know what an integral current is and what it means. What is the mass of that integral current? What is the mass of the other one? And what does it mean when we say A plus boundary B acting on tuples is equal to the push forward acting on a tuple minus the push forward acting on a tuple. So this definition is finally rigorous. And the key thing that I've added on this slide is that these guys are integral currents in the sense of Ambrosio Kierheim, acting on tuples. Recall, integral currents act on tuples of Lipschitz functions f pi 1 to pi m. So this push forward of m is well defined exactly this way. The boundary of B is exactly defined this way that we've discussed already. And now this page is well defined. And then we proved in our first paper that if mi are compact and the swift distance between m1 and m2 equals 0, then there is an orientation preserving isometry f from m1 to m2. So in sense, it is a distance in the sense that it's only equal to 0 when it's the exact same space. But what do we mean by saying that these are the exact same space? Orientation preserving isometry. So a pair of Riemannian manifolds that are oriented, they're oriented, not just orientable. They're not the same if they're endowed with the opposite orientation. Okay, so the distance between them is 0 if there's an orientation preserving isometry from one to the other. All right, so that's why it's a distance. The proof, I can't do the whole proof obviously in this tiny lines, but I just want to give you a feel of it. We show there exists phi i's from the mi's to z, such that phi 1 number m1 is equal to phi 2 number m2. So why do we have that? To get that, we are saying that this infimum is actually achieved. And it's achieved with an A plus boundary B, where A and B are 0. That's how we're saying there exists phi. So this line here is an entire theorem with about 10 pages proof. Why this infimum is actually achieved. Then we say, let phi be the phi 2 following phi 1 inverse. So we put them both into the same space. And now we're going to define our function f, our orientation preserving isometry, will be to take phi 2 following phi 1 inverse. This works because they have the exact same set. They are the same current, so they have the same set. So therefore, on this set, we can do this phi 2 following phi 1 inverse. Every point of positive density inside M1 is mapped to a point of positive density inside M2. Any other points that might exist in M1 or M2 can then be achieved by taking a metric completion on each side. F is Lipschitz. These are distance preserving functions, so this is also distance preserving. In general, phi 1 inverse is not defined. The only reason we're able to do this is because we're on the set. We're taking M1 to the set of this one, and then they have the same set. So now we can do this phi 1 inverse, phi 2. We need to define the Swift limit spaces, which will be the class of all spaces in which we can actually make this definition rigorous. So far, this definition is for pairs of oriented manifolds, but we want to define them for more general, larger class of spaces. All right, so let's look at our images again that we had discussed before. A sequence of Riemannian manifolds converge in the intrinsic flat sense to the following limit, which is an integral current space. Stefan and I looked at many examples before we came up with our definition of what an integral current space should be, but this example was one of the most informative to us because we saw the countability of charts here, and the total summing of the masses of the charts or volumes of each of these spheres was going to be finite. So we felt that we should be able to define an integral current space as a rectifiable set with some sort of orientation and weights. So the vague definition from Lesham 1 was that an integral current space is M rectifiable, which means it has countably many bileptrous charts, same dimension M, and it's well-defined M-1 rectifiable boundary, and the charts are oriented and have integer-valued weights. This was a vague definition. But now we can define integral current spaces rigorously because we can use the Ambrosia Kierheim theory to make this much more precise. Right, so remember, we're going to be setting up these bileptrous charts and things of the sort. So recall that the flat limits of Federer-Fleming of an orient submanifolds were integral currents. So remember what an integral current is. This is our definition from Ambrosia Kierheim. I'm just bringing up exact paste of what we had before because we don't have a blackboard that I can point to. Okay, so this is the exact definition from before. I want to be able to refer to it when I define our integral current spaces. So our key idea was that integral currents generalized oriented submanifolds in Z. That was the key idea of Ambrosia Kierheim, generalizing oriented submanifolds in Z. But now we want to generalize oriented Riemannian manifolds that are not sitting in an ambient space Z. They are all alone. Each individual Riemannian manifold is its own space. So what we defined was an integral current space is a metric space, XD, with an integral current T. Integral current T such that the set of T is actually equal to X. So we're demanding that we have a metric space XD, and on top of the metric space, we also have a T such that his set of positive density is the whole space X. We define the mass of an integral current space just to be the mass of its T, and the boundary of an integral current space to be the set of the boundary. So we look at XDT, we take the boundary of T, which is well defined by Ambrosia Kierheim. We know what boundary T is. That's something sitting inside X, so I make that a space, set boundary T. I restrict the distance from X, and I use boundary T for the current for boundary M. So this, if M happened to be a Riemannian manifold with boundary, this would actually be the boundary of the Riemannian manifold, the distance restricted from the manifold, and the charts for the boundary. It's important to note that this is the restricted distance. So on a Riemannian manifold, this distance was geodesic, as in every pair of points had a minimal geodesic between them, whose length is the distance. This distance is not having that. There are not necessarily geodesics in the boundary of M. This is the ambient distance inside M. With this definition, we end up that X is countably HM rectifiable because he's the set of something. He has to be countably HM rectifiable. He's actually covered by those charts that are used to define T. Now, if I give you a countably HM rectifiable metric space, if I say, oh, here's XD and they're countably HM rectifiable, that's not enough information to know what T is. T includes possibility of integer weights. T includes telling you which charts are oriented and which ones are opposite. So this T is more information than just the X and D. X and D is rectifiable, and they're covered by pairwise disjoint Lipschitz charts, actually by Lipschitz charts onto their images. That's the kind of XD we have, and T adds more information to that. It says that we have weights. If you know the integral current space XDT, you don't necessarily know what the charts are. You know that the charts exist. You can have a different set of charts that also exist, and the set of charts is called the parametrization, but it's not unique. There are other sets of charts that could also cover M, and there's other ways to put the weights down. But at every point in X, inside set Tx, there will be a unique integer that you can then use to define your mass of your space. This mass T would then be the sum where you took these absolute values of the integers. Any questions? All right. So keep in mind these integral current spaces are like metric spaces. They are individual and separate, and they don't live in an ambient place. An oriented Riemannian manifold is a metric space, MDM, that we've already talked about, with a smooth collection of charts, and the distances between points are infimums of lengths, and the volume of a set U inside the space is the Hausdorff measure. That's a Riemannian manifold. An integral current space, XDT, is a metric space XD, and an integral current T, such that set T equals X, where set T is the set of positive density for the measure defined by T. So it has a countable collection of bi-Lipschitz charts that are oriented and weighted by theta, which is a function from M to Z. And mass M of U is equal to this mass measure T of U, where the mass measure is now theta lambda HM. So while before volumes were just Hausdorff measures, now we have the theta coming from the weight, and lambda is this area factor that's between two constants. It might not be a connected metric space. It might not have even a single geodesic. Remember, we had that sequence of spheres with lots of long tubes between them, and that the limit was a sphere with the restricted distance from Euclidean space. That's an example of an integral current space that has no geodesics at all. No pairs of points have any geodesics at all. The boundary of the space is boundary M, dm. The current defined by boundary M is usually put the double brackets around it to emphasize this is the current that acts on tuples. The D is restricted from M. It's not the D of boundary M, it's the D of M. So even if the original M was geodesic and had geodesics between every pair of points, its boundary will most likely not have geodesics between points that lie inside boundary M. The boundary M is equal to the set of partial T, D, partial T. This is for the more general setting if it's not a Riemannian manifold. A compact-oriented manifold is an integral current space, M, dm, M, with weight theta equal 1, mass of U equal to volume U, it's HM of U. All right, that's just summarizing everything we have. And the boundary is this boundary, and it has a restricted distance dm. All right. Now we want to find the intrinsic flat distance between these integral current spaces. So I have a pair of integral current spaces, x1, d1, t1, and I'm saying that the swift distance between m1 and m2 is the infimum of the flat distance between them and z of the push forwards of the current structures, where these phi i's were distance preserving maps, where di was the distance used to define phi I. Here, phi number of t as acting on a tuple is equal to t of f following phi pi 1. So that's all well defined. And the infimum is taken over all complete metric spaces Z and over all distance preserving maps phi I from mi to z. And here's our old picture we've had all along. And this is the version with the weights now, where you will be filling in with A's and B's that are integral currents. But now we might need some weights on them so that we can really understand how to get from this weight to this one. All right. So this is all well defined now. Notice what we're pushing forward is the TI. The way to act on a tuple is what's pushed up forward. A is acting on a tuple, partial B is acting on a tuple, the push forward is acting on a tuple, minus this push forward is acting on a tuple. That's the information we're keeping track of. Not the specific list of charts, that's a parametrization, but how it acts on the tuples of Lipschitz functions. Any questions? All right, so it's the same image as before, it's just that now we know the rigorous definition. So this is the same as before, I just slid it up a bit. Here's the new theorem. If Mi are compact and the swift distance between M1 and M2 equals 0, then there is a current preserving isometry F from M1 to M2. So this is actually the theorem we proved. And in the case where Mi were oriented Riemannian manifolds, we proved that current preserving meant orientation preserving. But let's just show you a little bit about this. There's a current preserving isometry F from M1 to M2. That means that the distances are preserved. That's the isometry part. And that you push forward T1 to T2. Push forward T1 to T2 is what we mean by current preserving. So in the case when they're an oriented Riemannian manifold, this push forward is only pushing forward orientation. But for more general integral current spaces, this is also pushing forward all the ways. In fact, you could just push forward the charts from T1, from M1 to the charts on M2. Just okay. Proof idea. First, you show the infimum is achieved, so that there exists the phi i's that are distance preserving into some particular z, such that phi1 number T1 equals phi2 number T2. So that's just like before. In fact, this is the proof we do, and then the other one's a corollary. So the set of the two images are equal to each other, and F equals phi2 following phi1 inverse is defined. There's a couple typos here. I will fix them on the notes if you on these slides before you download them. All right, so it's the same proof as before. When we say the inf is achieved, we're saying that there's actually a z, there's actually a phi I, there's actually an a, and there's actually a b in that z, such that a plus partial b is equal to the swift distance, which is 0. Mass A plus mass B is equal to 0. That means mass of A is 0 and mass of B is 0. If mass of A is 0, you can show that A is 0. If mass of B is 0, you can show B is 0. So we have 0 plus partial 0 is this guy minus this guy. That's why we know that phi1 push forward of T1 equals phi2 push forward of T2. These guys are equal because the A plus the partial B is 0. That's what we mean by infimum is achieved in the setting where D swift equals 0. The infimum is also achieved in other settings, but in those settings, there exists phi I and there exists A and B, and you have this exact equality. That we did prove the infimum is achieved in all settings, but in the particular case where the infimum is achieved and it's equal to 0, we conclude phi1 number T1 equals phi2 number T2, that their sets of positive density are the same, and therefore we're able to set up this map to the z inside the set, then pull back out from inside the set over. All right, then we had the notion of a zero space. So what is a zero space? The zero space will be empty set. 0 is the distance between all points, and 0 is the integral current. 0 acts on a tuple by giving 0 out as the answer. So the swift distance is actually the exact same definition as we just had on the last slide. All I did was replace T2 with 0 everywhere. So it's well defined, and I don't need to write it as a special case. If M is Riemannian, then the swift distance from M to 0 is less than or equal to the volume of M. And that can be seen by just taking Z to equal M, phi1 to be the identity map from M to itself, A equal to the push forward of M into itself, and B is equal to 0. The mass of A, if A is actually the push forward of a manifold, its mass is actually its volume. When something is a smooth Riemannian manifold, its lambda, its error factor is 1, and its theta is 1. The weights are 1. An example is that the swift distance from a sphere to 0 is less than or equal to the volume of the sphere of one dimension higher divided by 2. Now, this is not an example of the previous theorem. What is this example saying? This is a new example. The swift distance from a sphere to 0 current is less than or equal to half the volume of a higher dimensional sphere. We're actually filling it in with a B to prove this example. Take Z to be this higher dimensional sphere. So phi 1 from SM to the equator inside the sky is distance preserving. Okay, the distance between points on the equator is exactly achieved by geodesics running inside the equator. Note that if I took Z equal to the disk, this would fail to have a distance preserving map phi 1 from SM to Z, because the shortest distance between points inside a disk is a straight line, not an arc. Okay, so we can't take Z to be dm plus 1. We wouldn't have a distance preserving map. Okay, that's fine. We'll take Z to be the SM plus 1. And then for my B, I'm just going to take the current defined by the upper hemisphere. So if I use the upper hemisphere sitting inside Z, then its boundary is just the equator. And we'll take A to be 0. So then let's see what we have. We have 0 plus the boundary B, which is the equator, is equal to the equator minus 0. Yes, that fits the rules up here. So if we have this, we have exactly found distance preserving maps. We've found a sample Z, and we found an A and a B. And if we use that, this will give us an upper bound on the swift distance, because we found an example. We're not saying it's the best. We found an example. And so this should be less than or equal to the mass of A. A was 0, so the mass of A is 0, plus the mass of B. What is the mass of B? It's the volume of the upper hemisphere, which is half the volume of the sphere, of one dimension higher. Are there any questions? All right, so this example I did was to really emphasize the point that this is about fillings. It's not just about volumes, regions of small volume disappearing. You're estimating swift distances also as how can you most efficiently fill in the volume between the space and another space. So filling in the volume from SM to 0 is filled in with this hemisphere. And we're going to use a similar thing to try to understand how to estimate the swift distance between points. All right, so I'm not going to go straight to estimating. This is just something to keep in mind for the future. Let's start with this slide here. Implications of swift convergence. If you have a pair of integral current spaces.
Sorry, Christina, there's a question in the chat from my colleague who is right near me.
Is the actual distance known?
Do you know the precise value of this swift distance?
No, believe it or not, this is actually an open problem for 50 years about filling in spheres. This is not known even for spheres.
Is it related to filling volume?
Yes, it's exactly related to the filling volumes. It's called the Pooh conjecture. Gromov talks about it in Filling Riemannian manifolds quite a bit. It's not proven. The filling volume of SM is an upper bound here. If we use filling, I'm going to talk about filling volumes. If we define filling volumes using currents, the swift distance will always be less than or equal from SM to 0 will always be less than or equal to the filling volume of SM plus 1. The filling volume defined even with chains is open question, even for spheres. For filling volume defined the way Gromov defines filling volumes with chains is known if you take SM with the Euclidean distance on it, then this is known to be the disk. That's like, I think, the only kind of filling volume. Certain very nice submanifolds of Euclidean space with restricted distances from Euclidean space, I believe, are the only known metric spaces whose filling volumes are exactly with the equality known. And this sphere one is an open question for over 50 years. It's very hard to get lower bounds. Any other questions? I believe it's called the Pu conjecture, Pu conjecture, that it's equal without Swift here, filling volume.
Yeah, Pu conjecture, yes.
Yeah, Pu conjecture. All right. All right, so I had mentioned already about how this infimum is actually achieved, but I want to talk about it when it's not just equal to 0 right now, okay? So you just have two Riemannian manifolds, or two integral current spaces, and you have this infimum, and you have a Swift distance, and we proved that the infimum is achieved. So you can choose a Z prime that's even nicer than the Z's in this class. You can actually take, the infimum is achieved on some Z with some A and some B. And we can define Z prime to be the set of A union the set of B, with the distance restricted from Z. This is separable in a rectifiable space. So this is actually a really nice class of spaces. Because it's achieved, we could actually say this definition is equivalent if we took the infimum not over complete Z's, but over separable and rectifiable Z's. Okay, so this is equivalent to that definition because we were able to prove it's achieved. And now we can use this fact to get more. If we have a sequence of MJs that Swift converge to M0, we would like to construct a special Z for the whole sequence. But what we have is a ZJ prime for each term in the sequence. And we have a ZJ prime, so the Swift distance from MJ to Z is actually the flat distance inside the ZJ prime. And this ZJ prime is nice, it's separable and rectifiable. But we have a different Z for every term in the sequence, and that can be very tedious and cumbersome. Now let's glue all these ZJs together along the image of the limit. If we glue them along this image of this limit, we get a complete separable Z made out of the ZJ primes. It's still separable. It's made out of the ZJ primes and a metric completed after that. We have distance preserving maps from Vij from xj to z. This is tricky to prove that these exist. This is not a short proof at all. I'm just giving you the quick intuitive idea. We get a complete separable z and distance preserving Vij such that the flat distance inside the z of the images converges to 0. So that also means the Vij number Tj acting on a tuple converges to phi 0 number T0 acting on a tuple. This theorem, which is in our first paper together, this theorem is very useful for getting properties or implications of knowing that a sequence converges. Because now we can put them all into a common space and then use all the properties that Ambrosia and Kierheim proved for currents inside metric spaces. So here we have a sequence of currents converging weakly to a limit current inside a single complete Z. These currents, therefore, have all the properties that Ambrosia and Kierheim proved hold for currents that have this. This is testing on all tuples omega. So using Ambrosia-Kierheim theory, Swift convergence implies the boundaries converge. We know that the boundaries of these guys converge, and then we pull back to get the information about the original integral current spaces boundaries converging. Okay, so these are the spaces converging. We now have the boundaries of the spaces are converging. In order to have this theorem, it was necessary for us to define that the boundary of an integral current space had the restricted distance from the original sequence, okay? That's why we had that strange definition for boundary. If you have a sequence that Swift converges, the limit of the masses is greater than the mass of the limit. That directly follows from Ambrosia Kierheim immediately. So we had the two properties we really wanted. You can say that at this point now, we basically have the key attributes of intrinsic flat convergence that we wanted when we made the definition in the first place. The first attribute was we wanted a sequence of manifolds to converge under very weak settings. We wanted boundaries to converge to boundaries, and we wanted to control the volumes, at least from above. for the limit. Remember, these masses are the Ambrosia-Kierheim masses. All right, so then we have this theorem. It says that if MJ Gromov-Hausdorff converges to MGH and the volumes are bounded below and the volumes of the boundaries bounded above, then there's a subsequence that Swift converges where the Swift limit is inside the Gromov-Hausdorff limit or the Swift limit is 0. I mentioned this theorem before, and now we can prove it. The proof is by Gromov's compactness theorem. We have the Gromov-Hausdorff limit to a compact limit. So he said you can actually produce a compact metric space Z and distance preserving maps to the compact space Z such that the Hausdorff distances are going to 0. So that's what we have from this part. All right, so we have the ambient space Z, and it's even better than our usual ambient space. It is not just complete separable, it is compact. That's very strong. Ambrosia-Kierheim compactness theorem said that if you had a bunch of currents who were sitting inside, whose set slide in a compact set, then, and they had upper bound on their mass and upper bound on the boundary mass, okay, which we have here. If you have those three, then there's a subsequence that, so that the currents converge to something, some T infinity. So now we have push forwards of the currents converge to some T infinity. We say that the set of T infinity, well, let's examine that. That's the set of positive density of T infinity. You can show if you have a point here with positive density for T infinity, then there had to have been points in the set of Tj that were getting close to it. So it's in the image of the limit of the phi jmj's. So it's in phi of Gromov-Hausdorff of the Gromov-Hausdorff limit. See, this, it's in this set inside Z. It's in this subset of Z. Okay, that's actually only a few lines proof to get that. So now we define that the Swift limit should be set T infinity, Z from Z, and T infinity. This is an integral current space. And we can see that the MJs converge to this Swift limit as long as we show that there is an embedding from the Swift limit into Z. Well, it's already sitting in Z, so we just take the identity map. And sure enough, we have the phi j number Tj's go to T infinity, so we can also show that the flat distance from Tj goes to T infinity goes to 0. So that's our M Swift. You might say, how is this inside the Gromov-Hausdorff limit? Well, he's sitting inside the distance preserving image of the Gromov-Hausdorff limit. So in that sense, yes, he's sitting inside the Gromov-Hausdorff limit because this is isometric to the Gromov-Hausdorff limit. So in that sense, he is sitting inside the Gromov-Hausdorff limit. Now, maybe he's 0 because Ambrosia-Kierheim's compactness theorem says subsequence converges to T infinity. Their T infinity might be 0. So if the Ambrosia-Kierheim's compactness theorem gives 0 as T infinity, then our M Swift limit is the 0 space. So this is very straightforward proof. And in our paper, we actually say this is a consequence of Gromov's compactness theorem, Ambrosia-Kierheim compactness theorem. It's not really any new theorem at all. It's a combination of these two with careful, precise explanation as to why each one of these steps works. Now, much more difficult to prove, and in an entirely different paper, Wenger proved this compactness theorem. So he proves that if you have a sequence of integral current spaces whose diameter is bounded above, whose mass is bounded above, and the mass of the boundary is bounded above uniformly, then a subsequent Swift converges to M Swift, and possibly M Swift equals 0. This theorem is very difficult to prove. It is not in any way a consequence of this combination, because this is now including sequences that don't converge in the Gromov-Hausdorff sense. He does sort of imitate Ambrosio-Kierheim's compactness a little bit, how they prove their theorem, but he has the fact that it's not sitting in a finite dimensional, it's not sitting in a compact set in Z, which they use very much so. So because it's not sitting inside a compact set inside a Z, he has to deal with this in a much more subtle way. He proves it by induction, building on dimension, and it's a beautiful theorem. I have to warn you that this theorem is not stated this way in his paper, because when he wrote his paper, integral current spaces weren't defined yet. But this is immediately a consequence of this paper once integral current spaces are defined. All right. So this is saying that we have this wonderfully huge class of manifolds that have Swift limits. But we also know that regions are disappearing, and we want a method to check which regions are disappearing. Would people like to have a break, or shall we move forward?
It's up to you to decide. I mean,
yeah, I mean, I'm going to start with some filling and more complicated things soon. But everyone's fine with this. I'll just keep going.
That's fine.
Okay. Okay, so we're going to use filling volumes to try to prevent a region from disappearing. A region which disappears could disappear because the volume is getting small, or it could disappear because a higher dimensional B can be found. So a filling for the region disappears. Okay, now when we mentioned filling volumes before, just in conversation, we were talking about global filling volume or the whole manifold. But right now we're going to have to talk about filling volumes just for regions inside, because some of the regions will disappear and some won't, and we want to prevent. To discover which does, we need to understand which regions have small fillings. So let me tell you about Gromov's filling volume. Portuguese was also a postdoc at NYU that I worked with, because CUNY is near NYU. CUNY is a public university, NYU is a private university. And so anyway, they have lots of postdocs. So Portuguese was a postdoc there, and he was interested in these problems with Gromov's filling volumes. But we're going to extend the definition from Gromov, and we're going to be taking the infimum over integral current spaces. So we'll define the filling volume in this setting of a manifold or an integral current space to be the infimum of the mass of one dimension higher integral current spaces whose boundaries are equal to M in the sense that they have current preserving isometries from the one to the other. Okay. So to remember that the distance on this boundary is the restricted distance from the big N. So we're having that the boundary, there's a distance preserving map here, and it's also current preserving. It's possible.
I'm sorry, that's the question in the chat.
Yes. Question in the chat. I'm not seeing these chat, even though I have chat here. Oh, here it is. There is discussion of Minkowski content in Wenger's paper. I don't want to make the exact statement here, but Wenger does address that. Sorry for the short answer, but it will be kind of long. Any other questions? Okay, for those of you who know about Gromov's filling volume, the infimum is not over all integral current spaces, it's over chain-like spaces. Chat. Oh, thanks. Okay. If you email me, I can actually point you to the exact place. Or you could email Stefan Wenger. All right, so Gromov's filling volume is not defined with integral current spaces. This paper predates Ambrosia Kierheim theory, and it's over chain-like spaces. And his infimum is not achieved, but this infimum is. Okay, so that's the advantage of using Ambrosia Kierheim theory to fill it in. We fill it in with integral current spaces, with the definitions of boundaries this way, and we use masses. The infimum is then an Ambrosia Kierheim mass, not a weighted volume. Gromov's has a weighted volume. So this is an interesting distinction. This should probably be investigated some more, but this is the version that we need in order to control Swift convergence. Okay, it is possible that this infimum is smaller than Gromov's. So I'm going to remind you again that the boundary of n has the restricted distance from n, from D, the restricted distance dn. So that's important to keep in mind. So what we're saying here is that we have dn of f of p f q equals dm pq for all p's and q's in xm, the x for the m space. And the push forward of, this should say t, I don't know what, this is a typo. Sorry about that. Push forward to tn equals tm. I'll fix all these typos and repost this online. So example, the filling volume of SM dsm. So sphere with the distance on the sphere and the integral current structure from the sphere is less than or equal to the volume of Sm plus 1 over 2 that we just talked about. And the proof is exactly what we just talked about, putting it inside the equator. That's giving it an upper bound. Open is whether this is equal to Sm plus 1 over 2. This is not exactly Poo's conjecture. But yeah, if this one is true, then Poo's conjecture will follow because, as I said, this filling volume would be even smaller than the other one. Probably equal. Example, if this filling volume equals this, then actually the usual filling volume is equal to this because it's stuck in between. Example, the filling volume of Sm with the restricted distance from the disk is actually less than or equal to the volume of the disk. Now, the Gromov filling volume is equal to the volume of the disk, I believe by work of Barago-Ivanov, maybe earlier work. The filling volume in our case, this is now a question, is it less than or equal? Okay, the proof is just taking the image of the sphere onto the boundary of the disk. As long as it's a restricted distance from the disk, then this is immediately distance preserving. But if it's a restricted distance from the sphere, it's not distance preserving into a disk. It needs a hemisphere. Theorem: if BPR is a ball in integral current space M, then for almost every R, we can make an integral current space out of the ball. We cut out the ball, we use the restricted distance from M, and we use the charts for the ball. This theorem says that for almost every R, this will be an integral current space too. And so is boundary of the ball. The boundary of the ball has the boundary of the ball, restricted distance from dm, and this boundary as the charts. Now notice, they're both restricted from dm, and if the ball is not convex, this is not equal to the distance inside the ball. That's something to keep in mind all the time. But this is what we need to control. The filling volume of the boundary of the ball will then be less than the mass of the ball. And this will allow us to check if the balls disappear or not. We can study the filling volumes of a sequence of balls and make sure that they don't disappear. Is everything clear in this statement here? I didn't write the proof. I'll talk a little about the proof later, but is everything here quite clear? Okay, we're going to be studying filling volumes of balls to try to prevent balls from disappearing, to figure out which balls disappear. Some balls will disappear and some won't. Okay, so I think I just copied what I had. Yeah, all I did was slide up. I got rid of the examples, okay? Recall, P is in set T if the limit as R goes to 0 of the mass of BPR divided by R to the M is bigger than 0. That's the definition of a set. I'm rewriting all the stuff because we don't have Blackboard, so I can't just point to them. The corollary is that P is in set T if the limit for the filling volumes is bigger than 0. The masses of the balls over R to the M bigger than 0, the filling volume of the boundary of Rm bigger than 0. So this was applied in my work with Stefan Wenger and with Medvedev-Portuguese to prove that M Gromov-Hausdorff equals M Swift if the MJs have a lower volume bound and Ricci bigger into H. So this is the non-collapsing Ricci case. We were able to prove MGH equals M Swift. Wenger and I proved it with H equal to 0, and Medvedev-Portuguese proved it with H negative. Also, Medvedev-Portuguese have a better proof, and I'm outlining their proof here. So you use work of Perelman and Kolding and Gromov to say that there is some constant M HV such that the filling volume of the boundary of the ball is bigger than this constant M VH over R to the M. This is tons of work, okay? But the idea is that Colding proved that if the volumes, that if MJs have these hypotheses, and you take the Gromov-Hausdorff limit, you have the volumes converging. And he also proved very strong control on the balls in the sequence. This is Colding. Colding did this. Perelman showed that you get a sort of uniform contractibility for the balls. And Gromov in his Fleming-Riemannian manifold showed that if you have that kind of contractibility, then the filling volume is bounded below, with constants that depend on the contractibility. A little extra effort to check on the scaling guarantees it's an R to the M here. This is crucial to get this R to the M. So we're combining three very powerful theorems from the past and examining them closely to get this. Now we use the corollary above about the filling volumes being bounded, this one, with the limit filling volume over R to the M greater than 0. Notice limit of this filling volume divided by R to the M is going to be CMVH greater than 0. We're having this true for all of our balls in our whole sequence with the same constant, because this constant only depends on dimension V and H. So the whole sequence has this property, and then we're going to add that we have these filling volume controls. If we get these filling volume controls, we will have that points are in the set, which means all the points of the Gromov-Hausdorff limit will be in the set, which will make the Gromov-Hausdorff limit equal to the Swift. If we can get all the points here inside the set, then the Gromov-Hausdorff limit and the Swift limit agree. All right, so we thought of all of this, and because of this thinking, we said, what we need to prove is that if balls Swift converge to V infinity, the filling volumes converge. So if you have this combined with this uniform bounds, we would be done with proving MGH equals M Swift. So on the next slide, I'm going to explain how Portuguese and I proved that if balls converge in Swift sense, then the filling volumes of the boundaries converge. Converge, no limits here. If you're just talking about masses of balls, we'd have a limit, and we wouldn't know if it dropped down to 0 at the end. It's the filling volumes actually converging that's going to give us the control we need to obtain when Gromov-Hausdorff limits equal Swift limits, when balls in a sequence don't disappear. So B infinity, if B infinity were 0, this would be 0. And the filling volume would go to 0. So the key idea is, if you want to show balls don't disappear, show their filling volumes don't disappear. On the next slide, I'm going to explain why we have this statement. Swift convergence implies filling volume convergence. These first 3 lines are justifying why we wanted to come up with this theorem. Okay, so we knew about Perelman, we knew about Colding, we knew about Gromov, we knew all this. And then we said, okay, can we use this? Oh, this Gromov thing works for our filling volume too. Okay, good. Can we use this now to tell us that we can control the limits? That's what we're going to do next. So filling volumes and Swift limits. The theorem says that MJM Swift converge to M infinity, which we can apply to balls. Okay? But the theorem says for any integral current spaces Swift converging to M infinity, the filling volumes of the boundaries converge. So proof. We need only show that for any fixed epsilon greater than 0, the filling volume of the boundary is less than or equal to the Swift distance plus the filling volume of the other boundary plus some epsilon. You see why? Because this Swift distance is going to 0, so we get the filling volume of this boundary less than or equal to something going to 0 plus the other guy. Epsilon's going to 0. So we get this guy smaller than this guy plus epsilon, and then we would just switch 1 and 2 to have the other side. So this is enough. If we prove this, we have the filling volumes converge. We're going to apply this to balls, but we're proving it in general for integral current spaces. Okay, the 4 steps have these 4 diagrams. I have the 4 diagrams up, and I'm going to start writing the steps of the proof. The first one says that by definition, phi 1, so I'm talking about with this picture here, this first picture, there's phi I from xi to z, okay, where an A and B, boundary B, such that the mass of A plus the mass of B is equal to the Swift distance plus a little error in case it's not achieved. So here's my M1, here's my M2. I filled it in with the yellow B, and A is these two little green pieces. This is really the exact same picture I've done for swift distances before, but I rotated it by 90 degrees. So this is our swift distance estimate. This is our estimate on this. And I'm not using it's achieved because actually we didn't know it was achieved yet at the time, or I don't remember why we did this. But anyway, you can say it's less than this plus epsilon over 2. Second one, this second picture. We know that mass of A plus mass of B is less than or equal to swift distance from M1 to M2 plus epsilon over 2. So what do we know about boundary of A? Well, remember A plus, we have right here, A plus boundary B is this stuff. So what do we know about the boundary of A? The boundary of A is the boundary of this guy minus the boundary of this guy minus twice the boundary of M, boundary of boundary M. Of B, sorry, boundary B. So this just comes from this line. I want to understand boundary of A better. Well, the boundary of the push forward is the push forward of the boundary. That's very easy to check on tuples. The boundary of the push forward is the push forward of the boundary. Again, easy to check on tuples. And it's very easy to check the boundary B. It's a little harder to check this, but boundary B is actually equal to 0 for any integral current. The boundary is 0. So now I want to construct a space N1. So here's my N1 here. N1 is the green stuff on the two sides made out of A. Set A, DZ, A. So N1 is made out of A. It's these two green pieces. And I have phi I that takes Mi to here. Oh, this should say boundary Mi. Boundary Mi to boundary N1. So the boundary of M, see M here is in pink, and the boundary is the two red dots. M is this light blue, and the boundary of M is the two blue dots. Okay, so we've just found a filling, a space N1M, who's filling in between the two boundaries. That's what we've done in step 2. Now, in step 3, we're going to talk about a new picture. We're just going to talk about the filling of the boundary of M2. M2 is in pink, and boundary of M2 are these two red dots. And we know, by the definition of filling volume, that there is this N2 here that fills it in. So there exists an N2, the boundary of N2 is equal to boundary M2, and the mass of N2 is less than the filling volume plus epsilon over 2. So we don't assume it's achieved. We have a little epsilon over 2 space. That's fine. And now the fourth step, we're going to actually glue this guy to this guy along the boundary of M2. So I take this blue picture, this picture here, and I put it over here. I take this picture and I attach it. And I'm going to take my green N1 here and my N2 that was purple, and I'm going to put them together to create a space N12. So I'm gluing the green N1 to the purple N2 along the boundary of M2. So along those two red dots, we glue them together and we get a space N12 of M. And the boundary of N12 of M, well, it's not here anymore. It's moved all the way over. His boundary is the two blue dots, which is boundary of M1. So now we have filled in boundary of M1. The filling volume of boundary of M1 is less than or equal to the mass of N12, which is less than or equal to the mass of N1 plus the mass of N2, less than the green part and the purple part. But the mass of N1 was the swift plus epsilon over 2, and the mass of N2 was the fill vol plus epsilon over 2. So together they get up less than plus epsilon, which is what we needed. And we're done with the proof. Are there any questions? There's one typo here. There should be a boundary. Once I see the video, I'll watch the video and fix all the typos. Is someone trying to speak? No. Okay. All right, so now we know that if a manifold swift converges to another manifold, or an integral current space swift converges to another integral current space, the filling volumes of the boundaries converge. But I already said that if you have swift convergence, the balls converge. So now we know that the fillings of boundaries of balls have to converge to fillings of boundaries of balls. So in this way, we're able to use the process we described before to prevent balls from disappearing. So we know, for example, for non-collapsing sequences with lower bounds on the Ricci curvature, nothing disappears at all. But in general, some points disappear and some points stay. And you can use this to determine which points are staying. You don't need to find an exact value for filling volume. You just need to know that the filling volume exists and is uniformly bounded. All right, so here's our theorem about the balls. The balls theorem is in this paper I wrote with Arzella Scoli in the title. If BP is a ball in an integral current space, then the balls of an is also an integral current space for almost every R. There's a theorem that I wrote with Wenger, which says that if they swift converge, we have the complete separable Z's, and they're all inside the common space C. And we have the theorem that if P naught is an M naught and MJ swifts to M naught, then there are, okay, this is a new theorem. Then there exist PJs and MJs such that the distance inside the Z of phi J PJ converges to phi 0 P0. So we're using the fact that there's this common space here to define what it means for sequences of points to converge to a limit space. So if you have a point in the limit, then there's a sequence of points in the sequence whose images of those points inside that common space Z converge to 0. This sequence depends on our choice of phi j's. Okay, this PJ depends on the choice of phi j's. Furthermore, for almost every R, the subsequence JK such that the balls converge about those points. So now we know what we can talk about when we say that balls converge to balls. If there's a point in the limit space, you can find PJs in the sequence whose balls will swift converge to the ball about that point in the limit. And in particular, limit of the mass of the balls is bigger or equal to the mass of the limit ball, which will be positive if P is actually existing. If this limit ball exists, this mass is positive. As a corollary, the boundary of the balls also converge, and the filling volumes of the boundaries converge. This is just a greater than equal with the limit, and this is an actual convergence. That's why this one is stronger. This one's stronger at controlling things because it's actual convergence. This one could suddenly drop to 0 in the limit, even if the PJs all existed. It's possible there's no P0 in the limit. We also know that the diameters of the M0 is less than or equal to the limit for the diameters by examining these points. If I have 2 points in achieving the diameter in M0, then say, let's call them P and Q, then we have PJs and QJs in diameter MJ, and the distance between the PJ and QJ converges to the distance between P and Q. And so the limit for the diameters is bigger than or equal to this. It's possible the diameter is larger and there's some extra points further out that disappear, that we're in thin wells. So if one assumes that there's a swift limit who's not 0, this theorem has been proven basically using the same idea and the same process as this one over here with PJs, but doing all points at once. So you show that if MJ swift converges to a swift limit that's not 0, you have the complete separable Z and all these distance preserving maps into Z, and then you get the convergence inside Z of images of MJ. And what this says is that you can then find domains inside MJ where the domains Gromov-Hausdorff converge to the swift limit. And the limit for the mass of the domains is bigger or equal to the mass of the swift limit. So the whole way to try to prove something like this is to sort of say, okay, this is chopping off wells. The thin wells that disappeared, the thin regions, the regions that have small volume, we're just going to cut them off. And if we cut them off, we actually get a Gromov-Hausdorff convergence sequence, and it has enough mass. So this theorem is a more solid theorem that kind of captures the fact that there are points. If you have points in the limit, then there's sequences of points in MJ. These sequences of points in MJ that converge to that limit are also lying inside this domain that has a Gromov-Hausdorff limit. So this last theorem has a lot of potential, but you might say, I haven't proven it at all. I mean, before it kind of made sense about having one point at a time, but having a whole region converging in the Gromov-Hausdorff sense means we have to control this NJ very strongly. And so actually the proof of this theorem, and also the proof of the balls, and also a lot of the main theorems here, which is the balls converging, where is it? This one, this ball's converging, and this one, both need the Ambrosia-Kierheim slicing theorem. So I'm going to have to teach you that slicing theorem in order to justify everything. So this is the Ambrosia-Kierheim slicing theorem, and it's based on an earlier slicing theorem by Federer and Fleming. And the idea is to slice up your manifold, to cut it, cut into many pieces, all right? So you're given a Lipschitz function f from our metric space Z to R, and we have an integral current T inside Z. So here's my metric space Z, and I have this integral current that I draw like a submanifold. So T is this light blue thing. I've tried to draw orientation to it, and boundary T is running around the outside of T. So that's what we're given. We're also given that there's this Lipschitz function f that is taking Z over to a real line. And now for almost every S in the reals, we're going to define a slice of T by f at S. I'll just show you in the picture what it is before we describe it here. The slice of this light blue T for this S is this line here. We just gave it a slice. If you change S, you'll get more lines, and we sliced it up into lots of slices, like slicing a loaf of bread here. Slice, 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 slice. So here's a slice. And this is the notation for the slice, TFS. And now I'm going to rigorously define. So the rigorous definition involves restrictions. So let me just say, S restricted to U, to a set U, a current restricted to a set U, which is denoted S restrict U, acting on a tuple, just means S, indicator function of U times the H, and the rest of the pi ones. Indicator function is 1 when you're inside U, and it's 0 when you're not inside U. Indicator function U times H is no longer Lipschitz, but they do make this make sense. And basically, the idea of the restriction is to say, we're not interested in the part of S that is not on top of U. So here in light purple, I have T restricted to F inverse S to infinity, and that's this part. F inverse S to infinity is everything above this line S. This is F inverse S. Everything above that is F inverse S to infinity. And T restricted to that is the part of the submanifold that's actually above the S line. So that's T restricted F inverse S. So that's this notation right here. All right. What is the slice? Well, the slice, I want to make something that's one dimension lower. We have a way of saying, I only want to look at this part of it for a domain like this. So we're going to say, what is the boundary of T restricted to this? So the T restricted to this is this light purple part. Its boundary is go around here and across here and around top. That's its boundary. All right, but we're going to take negative its boundaries. That means just go around the other way. Or around this way. Negative the boundary is going around the other way. Around this part where it's restricted. Then it says, add the boundary of T. What's the boundary of T? This dark blue part. Restricted to F inverse of S. Okay, so the boundary of T restricted to the top half is this stuff. Boundary of T restricted to F inverse S. It stops there. Starts here. Stops here. So I'm taking this negative boundary, which was going this way, and I'm adding this dark blue part from here to here, and that leaves us with just this purple slice. Okay, the purple slice starts here and ends there. Okay, so this is a well-defined thing. It's their theorem that it's an integral current. Okay, it's a theorem that this is an integral current. So what do they need to prove to show that this thing is an integral current? It's a current. This sort of thing is giving us a current. It's something that acts on tuples. and it's one dimension less than t, because it's made out of boundaries. And now they want to say, why is it an integral current? Just because you have charts covering t and charts covering boundary t, why should you have charts covering this? So to prove it's an integral current, they control its mass. They have a theorem that says when you can bound the mass, you can get integral current to obtain an integral current. So they prove its mass, and the mass of the boundary is finite for almost every S and R. That they're only able to prove for almost every S. There are examples where there are bad S's. What you could imagine for an example with a bad S is if this submanifold actually stayed flat for a little while inside the S level before going up. Then the mass would be higher dimensional in some sense. The Hausdorff measure would be too large, and the mass would not be finite. If the surface stayed at this level and then continued upwards, that would be a bad level. But this says almost every level, almost every S and R, you end up with an integral current, and the boundary of the slice is equal to the slice of negative the boundary sliced. So we have control on the boundary. They control the mass of the slices and the mass of the boundary. In fact, they show that the masses integrated is equal to the mass of T restrict dF, which is less than or equal to Lipschitz F times mass T. And here, mass restricted T restricted dF, what this means is you take your h pi 1 to pi m minus 1 and you stick in the f here. So it's like h df wedge d pi 1 to d pi m minus 1. Okay. T restrict df is a higher dimensional. All right, this mass bound is basically how they get, if the integral of the masses is bounded, once they have this is bounded, they get the almost everywhere S's out of this kind of bound. And they do the same thing for boundary T. They apply boundary T to this, and they have boundary T here to get controls of the boundary. So first they get rectifiable, and then they get integral. All right, any questions on this?
Sorry, Christina, we really need a break very soon. So
okay, I was going to have a break whenever you want. So
no, but this would be the final break. We still have 2 more lectures after to follow. It's
Can you
well, what, I thought my talk ends at. I'm confused at the end time.
It's 15 minutes over.
I'm 15 minutes over.
I'm sorry, I should have.
Can we continue this today?
So, I'm very sorry. I'm sorry. No, I can stop here. I can stop here. I didn't realize it was 15 minutes over. I'm sorry.
No
I'm
problem.
very sorry. Yes.
That's fine.
I'm so sorry. I didn't realize I had the wrong time in my head. All right. Thank you so much. And we will finish tomorrow.
Thank you very much. I apologize for stopping you.
No, don't apologize. You could have stopped sooner. Sorry. Yes.
So probably you postpone the proof of this slicing theorem tomorrow or anything like this. So
no, I'm going to just apply it. Yes.
Yeah. Okay. Very good. Are there any questions? Very quick questions. Okay. If this is not the case, thank you very much. And
thank you. I'm really sorry to go over. Yes.
Tomorrow you'll be the only speaker, so you could talk 3 hours. It's no problem. Okay. Bye, Christina.
All right. Bye. Thank you.